So what we are going to do is that we are going to take up an example involving this important theorem in which we know that if we change the order in which we take partial derivatives of this function f, then the partial derivatives are equal. So just to reinforce the idea that they are equal under certain conditions, which mostly prevail in the cases that you get, but still there is an example that we are going to look at, which will show that they may not always be equal, and when they are not equal, because this is a condition for their equality. So to illustrate this, I'm going to take up this function, and we are going to look at the mixed partial derivatives, just these two. I mean, there are many ways to write mixed partial derivatives, and show that these may not be equal to 0. So what we will do is, let's recall the way we calculate partial derivatives from definition. And we are going to use these definitions from our free textbook, okay, the OpenStax textbook that we are using. So here is the function, and this is the definition that we have. And what we would like to do is to calculate the partial derivative and mixed partial derivatives at this point 0, 0. And even here, if you notice, what we got is this, that is, this actually defines how to take partial derivatives, or tells us how to take partial derivatives at any point x, y. So what we are doing here is that we are calculating it at 0, at 0, 0 rather. So let's just put this in perspective. Here you go. This is the limit, and now what we have to have is x is 0. So if x is 0, this is out, right? And this is 0, and y is 0 as well. So 0 and then 0, 0. So what we have is this, simply that f0, 0, is 0, okay? And if you look at fh0, so that goes in this territory, because when we are taking the limit, we may just stay away from the particular value where we are taking the limit. So in this case, what happens is, let's bring this over, and once we bring this over here, what we have is, since x is 0, this whole thing will, since y is 0, y is 0 right here. So this whole thing is going to become 0 because it's multiplied with that. And for x, I have h. So I got h squared here. And again, as I said, at the moment, we may treat h as different from 0. So here what will happen? This is going to become 0. So this is 0 minus 0 over h. So that will be 0. And so the partial derivative at 0, 0 is 0. And with respect to x, of course. And this is not exactly symmetric in x and y. But even if you did this, like wrote partial derivative with respect to y, what that is going to change to is this. That is, let me just quickly do that for you. That, remember this, if we go back to the definition, here I think the book decided to write k, so I'll write k. And of course, this has to be k going to 0, and you can fast forward if I'm boring you, because I'm boring myself right now, repeating the same stuff. So what happens now is this. I don't know why I chose to write all that. That's okay. So this will become what? Since x is 0 now, so this whole thing is 0, okay? And this is k squared, all right? And this part is 0. Oops. So this part is 0, and that again becomes, simply exactly what we had before. I don't know which way will be faster, copying, pasting, editing, or writing directly. So this is what we have, and 0 over k is going to be 0. So the partial derivatives from the with respect to x and with respect to y are equal in this case. Okay. So now we would like to calculate this quantity, and which is the same as df dx, again differentiated with respect to y. So before we do that, we have to have df dx in a function form. So first let's calculate, sorry about that, let's calculate df dx when x, y are not at 0, 0, because remember there we have a problem with the denominator. Okay, so we got d dx, okay? And when we are calculating the partial derivative of this, and I shall not really take you through all the algebra. So first it will be easier if we did this, that if we distributed xy over x squared minus y squared, because that way it'll be much easier to handle. So let me just change the numerator into the expanded form. Okay, so here we are. All right. And then how we would proceed is that we will just go by the quotient rule, square the denominator. Okay. And then what we do is differentiate the numerator with respect to x. So that gives us, if we look at this, 3, not 4, 3x squared y, right? And then the sorry about that here, y minus, now derivative of x is simply 1, so we will have only y cubed left over here, and then we will just put the denominator as it is, and then we will differentiate the denominator with respect to x, of course partially, and then write the numerator as it is. Now let's let the computer do the algebra. Okay, it could have done the partial derivatives too, but we need some practice, so that's why I decided to do it this way. So expand, so this is what we get when we expand it. So what does it become then is, it is simply x to the 4y and etc., etc., and divided by x squared plus y squared square. So now what we are going to do is, now I'm erasing this. Okay, now let's do one thing real quick that might come in handy. That is, you can see y is a common factor in the numerator, so let's factor it out, and then when we do that, what we shall have is that we shall have y is out, this becomes 2, and this becomes a 4. So now we would write df dx as a function of x and y. So let's just do that, df dx is going to be this quantity, right? If xy is not equal to 0, 0, right? Okay, and what did I do? Right, is not equal to 0, 0, and so here we are, and it is equal to 0 if xy is equal to 0, 0. So what we are going to do is that we are going to take the derivative of this function with respect to y at 0, 0. So let's just do this, just for convenience sake, let's just call it capital F x y. Okay, and let me change the fonts here. Okay. Here we are, equal to. Okay, and likewise you can find that, I'm not going to go through the whole calculation again, that is we can ask it for ddy, and I'm asking it in right here. We can do it in MATLAB if you don't have access to this package. Okay, so which is okay. MATLAB will do that, and I'm going to show you how to do that with MATLAB. So here I did this, so it gave us a similar format. So what I will do now is that I shall write first, let me change this to G, and now what I'm writing is that I'm writing df dy, because this I will be differentiating with respect to x. So that quantity equals this if xy is not equal to 0, 0, and I think we can bring it up here. Wouldn't hurt, okay? So this is when xy is not equal to 0, 0, and we know it is 0 at 0, 0. So let's just write it as a piecewise function. So now gxy equals, for x equals not 0, 0. Okay, this is this function. So let me just write an if here. Okay, and it is 0 if xy equals what? If xy equals 0, 0, let me just bring it down from here. Okay, so what you notice is this, that when you are looking at 2f, because we have to look at this d2f dy dx, okay, so dy dx, so that will at 0, 0. So that will amount to what? As we saw just a while ago, that's the same thing as this. This is what we are going to get. So that's the same thing as this. And then what we had done is that we had changed the notation for this by f. So that will be your big F. And just to let's align this a little better. We can do this right here. We can write f right here. Okay, so we want to calculate this quantity, and we know who f is, or big F. It's right here. Okay. So this is our capital F. Okay, and that was G. So what you will have is that, say you are trying to obtain this. Now we are differentiating with respect to y, so we will go in the same fashion as before. That is for partial derivative with respect to y. We used this, right? Okay, just to use it just by primary definition, not just algorithmically. Okay, and this changes to who? Big F. This also changes to big F here, sorry. Okay, good. So what you have here is that you shall substitute k for y and 0 for x. And what will happen in that course? Once you do that, all these have x in there as a factor, so they will become 0. And y is k, so this is k. This is negative k to the power 4. So what we get on the top is, just a moment, what we get on the top is this. That is, we get k times negative k to the 4, because that's what y is being replaced with. Okay. All right, negative k to the 4. And then again, actually, let me change it, because this is the numerator there, right? And in the denominator, what we have? X will be 0, so k square would be k to the power 4. All right, and then we have k on the bottom. Okay, so these two will cancel, this k to the 4, k to the 4. So what we shall have is simply negative k over k. Okay, and those k's will do what? They will cancel each other. So this just comes out to be negative 1. All right. Now, when we go for the other direction. That is, when we go for this, it'll go exactly the same way. So you don't have to listen to me if you don't want. All right. Okay. So here you go. You got this. And this will again be as before, I think, since I already had the notation. So let me just take advantage of that. Okay. Just by copying and then editing here. Okay. So here this changes to y, this changes to x, and and this changes to what? G, because that's what that was. And this is changing to x, and G here. So what we did was we just copied the earlier steps and just changed the notations. And if you do this, remember who G is. G is, where are you? G is right here. Okay. So G is simply this. So if I did this, if I calculate dg dx at 0, 0, then it'll be the same style. And the only thing, so this whole thing will become 0 because y is a factor and y has to be 0. And then as before, this is the limit that we are calculating. Now y is 0. So what that will do is this. First of all, this whole thing will be 0, as you can see. And then here y is 0. So what that's going to do is that will erase this whole part for us. And this x is how much? H. So what this becomes then is this, that after the substitutions, as I said, I'll do the substitutions right here. This is 0. And then we got here, this is H, right? This is H as well. And since y is 0, all these guys, they disappear. Okay. And then here, y is 0, so that's out. And this is H. Okay. Oh, one moment. Let me increase the font size here. Okay, so that's H. Okay. And then what happens is that we got, see, negative is positive here. So we have H to the power 5 over H to the power 4 here, and then we have an H downstairs. So that will be H to the 5 over H to the 5. That will be 1. So what we find is this, that the second derivative taken in this manner is how much? That's a 1. But we saw just a short while ago that if we go the other way around, it will be -1. That is, if we switch the order in which we took the differentiation, what it becomes is that it becomes a -1. And you can see, so these are different, and you can see that even though these two turned out to be different at 0, 0, these guys are not continuous at 0, 0. Okay, just to show you. So I'll include the commands in the description window. But this is a second derivative, and when xy is not equal to 0, 0, either way it will be the same. So here, if you took, say, x equals r cosine theta, like change it to polars, and y equals r sine theta, then what will happen is that here, this is a polynomial of degree 6, this is a polynomial of degree 6, so r to the power 6 will just cancel in the numerator and denominator, and the limit at 0 will depend on the theta, on the values of theta, that is that is along your approach. So it wouldn't have a limit and consequently it wouldn't be continuous. All right.